You know, right now, the biggest tech companies in the world are they're spending billions of dollars building these quantum computers that basically look like massive freezing golden chandeliers.
Yeah, that's exactly what they look like.
Right. Like if you haven't seen a picture of one recently, just imagine walking into this state-of-the-art laboratory and dominating the entire room is this giant cylinder just suspended from the ceiling.
It's usually surrounded by thick cables,
Okay.
right? And humming machinery and just miles of plumbing.
Exactly. It's called a dilution refrigerator, and it requires entire separate rooms just for the compressors and pumps alone.
Oh, easily.
And just to put it in perspective for you, it draws up to 26 kilowatts of power, which is, I mean, that's enough electricity to run an entire neighborhood of
It's a
homes.
massive power draw.
And what is all of that infrastructure actually for? It's
Yeah.
literally just to keep a tiny microscopic chip at the very bottom of that chandelier cold enough to hold a few dozen quantum qubits stable for just a fraction of a single second. It really feels like we're using this industrial wrecking ball to crack open a microscopic nut.
It is the absolute definition of an infrastructural bottleneck. I mean, the irony of current quantum computing is that we've engineered these incredibly delicate, beautiful quantum states, but the life support system required to keep them from collapsing is just completely unsustainable.
Right.
When you look at the energy consumption and the sheer physical footprint of those dilution refrigerators, you realize very quickly that you cannot scale this approach. You can't put a 26 kilowatt golden chandelier on a desk, or in a standard server rack.
But what if I told you the future of quantum computing isn't a giant freezer? What if, instead, the most powerful quantum computer on Earth is basically a 3D printed ball of carbon that fits on your laboratory benchtop, runs on the power of a standard kitchen appliance, and actually actively cools itself?
It's hugely.
Welcome to today's deep dive, because we have a really fascinating mission ahead of us. We are looking at a paradigm shift that completely upends the last 20 years of quantum hardware development.
It really does.
We're going to unpack the step-by-step roadmap for building exactly that kind of device. Our source material today is the April 2026 technical white paper titled Quantum Sphere. And I want to set the stage for you here. This document isn't just theoretical physics.
No.
It's not some pie-in-the-sky academic wish list. It is a literal instruction manual.
And that's a crucial distinction to make. It's an engineering roadmap. We are essentially moving away from massive brute force cryogenic engineering and stepping into an era of highly elegant materials-driven design.
Yeah, and we're going to explore the miraculous properties of graphene, the physics of something called invisible magnets, and how this system creates built-in cooling systems that completely kill the need for that giant dilution fridge.
Right.
Plus how a single sphere scales up to this sci-fi sounding concept called a Quantum Dyson Sphere packing 1,000,000 qubits. But to build a house, you need to understand your building materials first. And the foundation of this entire architecture comes down to a single layer of carbon atoms.
Yeah, and before we even touch the carbon, we really need to understand the structural flaw in how we currently build quantum computers.
Okay.
Because if you look at the quantum chips making headlines today, like IBM's Condor or Google's Sycamore, they all share this fundamental architectural constraint. They are planar.
Okay, let's unpack this. By planar, you mean they are flat, right? Like two-dimensional surfaces, like a standard computer chip you'd find in your laptop.
Correct. They are built on flat wafers of silicon or sapphire. And when you have a flat chip, all of your wiring has to be routed along that two-dimensional plane.
Makes sense.
In a quantum computer, you have microwave control lines coming in to manipulate the qubits, and then readout lines coming out to measure them. Now, if you have 50 qubits, you can just barely manage to route those wires from the edges of the chip to the center without them crossing over one another.
Right.
But what happens when you want to upgrade to 1,000 qubits or 10,000?
You just run out of physical real estate. I mean, it's like trying to build a massive, sprawling city highway system. But a bizarre zoning law dictates that no roads are allowed to go over or under each other.
Yeah, exactly.
No overpasses, no tunnels. Eventually, you can't build any new roads to the center of the city without plowing through an existing highway. You just get a massive traffic jam.
I take that analogy a step further, actually. It's not just a traffic jam. The cars themselves are highly volatile and prone to exploding if another car drives too closely to them.
Wait, really? Exploding?
Oh, metaphorically.
Yeah.
In a flat quantum chip, packing wires tightly together causes electromagnetic interference between them. We call this wiring crosstalk.
Okay.
And crosstalk leads directly to decoherence. Decoherence is the arch nemesis of quantum computing. It is the moment, the fragile quantum state of the qubit, the state where it can actually perform those miraculous calculations, collapses back into boring classical reality.
Oh, wow. And the wiring traffic jam isn't the only thing causing that collapse, is it? Because the white paper points out that a lot of this decoherence actually comes from the flat chip itself,
Yeah.
the substrate.
Yes, absolutely. Think about how a traditional planar chip is manufactured. You start with a flat silicon or sapphire wafer. Then you deposit layers of aluminum or niobium to create the superconducting circuit.
Right.
Then you might use other materials for insulating layers. These are completely different materials with entirely different atomic structures.
Okay.
When you take that multi-material sandwich and freeze it down to near absolute zero in a dilution refrigerator, those different materials contract at different rates.
Oh, I see.
This creates thermal mismatch. The physical stress literally tears at the microscopic interfaces between the metals and the silicon.
So the chip is essentially fighting against itself as it freezes.
Exactly. That thermal stress, combined with microscopic impurities at the boundaries where the aluminum meets the silicon, creates an incredibly noisy environment. It generates tiny vibrations, stray electrical charges, random magnetic fluctuations.
It sounds chaotic.
It is. We call it substrate noise. To the delicate qubits sitting on top of that wafer, it feels like they're trying to do high-level calculus in the middle of a heavy metal concert during an earthquake.
That's quite the image. Enter graphene. The Quantum Sphere white paper proposes throwing away the flat silicon wafer entirely and relying on graphene. Now, we've all heard the hype about graphene for years. It's a single layer of carbon atoms arranged in a hexagonal lattice, like chicken wire.
Right.
But the statistics listed in this paper frankly look like typos to me. Let me just share these numbers with you. The current density, which is how much electricity you can push through a given area, is 10 to the 8th to 10 to the 9th amps per square centimeter.
It's massive.
The paper notes that is more than 100 times better than copper.
It is. If you tried to push that much current through a microscopic copper wire, the copper would instantly vaporize from the heat. Graphene just handles it effortlessly.
That's insane. Then there is the electron mobility, which sits at around 200,000 square centimeters per volt second. The thermal conductivity is 2,000 to 5,000 watts per meter Kelvin, which is literally the highest of any known material. It can move heat incredibly fast.
Yes.
And on top of all the electrical and thermal properties, it is physically the strongest known two-dimensional material with a Young's modulus of about 1 terapascal.
Let's translate that Young's modulus of 1 terapascal into physical reality, because
Right.
that's the number that really makes this entire architectural leap possible.
Okay, let's do it.
Young's modulus measures a material's stiffness, its resistance to being stretched or deformed.
Mm.
A terapascal is exceptionally high. For context, structural steel, the stuff we build skyscrapers and bridges out of, has a Young's modulus of about 0.2 terapascals.
Wow.
Diamond is around 1 to 1.2 terapascals.
Wait, so this single layer of carbon atoms is fundamentally as stiff as diamond?
Precisely. Yeah. But what the quantum sphere architecture does so brilliantly is that it doesn't just use graphene for one of these properties. It doesn't just use it as a strong wall or just as a good wire.
Right.
It leverages all those extreme properties simultaneously. In this design, graphene is basically playing triple duty.
Okay, let me try another analogy here. It's like an architect deciding to build a skyscraper, but instead of using concrete for the walls, copper for the electrical wiring, and separate silicon computers for the offices inside, they invent this magical new building material.
Okay?
And this single material acts as the rigid structural walls. It also safely carries all the high voltage electricity for the building, and it actually acts as the computer processor itself.
That's a really good way to visualize it, but it actually goes one step further in terms of engineering elegance. When you build a system out of a single material, you achieve what the white paper calls unity of material.
Unity as material.
Okay, let's look at those three roles in the quantum sphere. First, because of that extreme current density, the graphene acts as the electrical conductor, carrying massive currents to generate magnetic fields.
Right.
Second, because it has that diamond-like terapascal stiffness, it forms the rigid structural shell of the computer. It doesn't need a separate metal chassis to hold it together.
That makes sense.
Third, at the very center of the sphere, the actual quantum processor, the qubits themselves, are made of bilayer graphene quantum dots.
So instead of gluing aluminum and niobium onto a silicon wafer and hoping they don't rip themselves apart when they freeze, you just use carbon for the house, carbon for the wires, and carbon for the brain.
Yes, and by
Yeah.
doing that, you completely eliminate thermal mismatch. If the entire machine is made of carbon, every part of it expands and contracts at the exact same rate when you change the temperature.
Oh, wow.
You eliminate the chaotic interfaces between different materials.
Yeah.
The earthquake stops. The heavy metal concert goes silent. You've created a profoundly quiet, stable environment for your qubits to operate in.
But that brings up a massive question for me. If the outer graphene shell is acting as the wiring, what exactly is that electricity doing? Because the white paper states that the outer shell generates a very specific, highly protective magnetic field.
Yes, it does.
And this leads us to the geometric magic of what they call the Spherical Halbach Array.
Right. To manipulate the specific type of qubits they use inside this core, you need a highly uniform, perfectly stable magnetic field. Now, historically, if a physicist needed a strong magnetic field in the lab, they'd bring in massive, incredibly heavy superconducting electromagnets made of giant coils of wire, or they would use huge permanent magnets.
Right, which goes right back to our problem of giant room-filling infrastructure. But the quantum sphere uses a Halbach array to generate this field using only a microscopic layer of carbon. What exactly is a Halbach array, and what is the rotating magnetization principle?
To understand a Halbach array, imagine holding two strong refrigerator magnets. If you try to push the north poles together, they repel each other. They want to flick around.
Yeah.
Now imagine you have a line of dozens of little magnet dipoles. Think of them as tiny compass needles. In a standard magnet, all the little needles point in the same direction, say straight up.
Okay, got it.
But in a Halbach array, you force those needles into a very specific unnatural pattern where the direction of the magnetism continuously rotates as you move down the line.
The paper actually provides the math for this, describing a linear array along the x-axis. It gives the equation for the magnetization vector as m of x equals m, 0 times the vector sign of k prime x, cosine of k prime x, 0. I mean, I know that just sounds like a blur of trigonometry, but what is that math actually describing in physical space?
It's describing phase quadrature.
Phase quadrature.
Don't let the jargon intimidate you. Think about two ocean waves rolling toward the beach. The sine wave and the cosine wave are essentially the exact same shape, but they're offset from each other. They're out of phase. When you arrange magnetic forces using this specific offset math, they interact with each other in a highly asymmetrical way. On one side of this line of magnets, let's call it the inside of the magnetic fields, from all those differently angled little compass needles align in a way that reinforces one another.
Oh, I see.
The peaks of their invisible waves stack up. This is called constructive interference.
So on the inside, the magnetic field is boosted, it becomes incredibly strong and uniform. But here's where it gets really interesting. What happens on the outside of that line?
On the outside, the offset waves hit each other at opposite points. A peak meets a trough. This creates destructive interference. The magnetic fields perfectly cancel each other out.
That's wild.
So as a result of pure geometric arrangement, you have a massive, strong magnetic field on one side of your material and literally zero magnetic field on the other side.
It's exactly like noise-canceling headphones, but for magnetic fields. Like the headphones listen to the ambient noise of an airplane engine, and they instantly generate a sound wave that is the exact mathematical opposite. When the two sound waves collide, they cancel each other out to zero, and you hear silence. The Halbach array is physically arranged, so the magnetic noise on the outside cancels itself out to zero.
That's a spot-on comparison. It creates what we call a one-sided magnet.
Yeah.
Now, we already use versions of this technology in the real world. If you look inside the bore of a high-end MRI machine or the inside of advanced brushless motors, they use cylindrical Halbach arrays.
Right.
They arrange permanent magnets in a circle to concentrate the magnetic field inside the tube while keeping the outside of the machine relatively field-free.
But a cylinder is just a tube. It has open ends.
And that's the fatal flaw for quantum computing. At the open ends of a cylinder, the magnetic field leaks out. The lines of force bend and distort. Physicists call these end effects.
Oh, okay.
And remember, our fragile qubits require an absolutely perfect uniform field. Even a tiny distortion at the ends of a cylinder would cause decoherence.
So if the leaky ends of a tube are the problem, the solution is just to close the tube up entirely. You just wrap the cylinder around itself in 3 dimensions. You make it a sphere.
Exactly. The mathematical extension of the Halbach array from a cylinder to a sphere is brilliant because it eliminates end effects entirely. A sphere has no edges.
Right.
If you map that continuously rotating magnetization pattern perfectly over the unbroken surface of a sphere, you get a completely uniform, perfectly contained magnetic cavity inside. The white paper states it achieves greater than 99.9% uniformity.
Wow.
And on the outside of the sphere, complete magnetic silence, zero field.
Which means it inherently shields the inside from the outside world. You don't need to wrap the computer in massive layers of lead or highly specialized metal vaults to protect it from stray magnetic fields in the room, because the geometry of the sphere itself actively cancels out outside interference.
Yes, but remember earlier you pointed out that traditional magnets are heavy and bulky. You can't build a microscopic, benchtop quantum computer using chunks of heavy metal permanent magnets. Furthermore, permanent magnets are static. Once you manufacture a permanent magnet, its field is fixed.
You can't change it.
No. If you need to fine-tune the magnetic field to calibrate your qubits, you can't just easily turn a dial to change the permanent magnet's strength.
So how are we making a spherical, one-sided magnet without actually using heavy, permanent magnets?
This is where we circle back to the miracle of graphene. Because graphene can handle those massive electrical currents that 100 times better than copper current density, we don't need physical magnets.
Oh, I see.
Instead, we use highly focused lasers to draw microscopic conductive paths directly onto the surface of the graphene shell.
Like drawing a circuit board.
Yes, but a three-dimensional one. By running specific controlled electrical currents through these intricate laser-drawn paths, we simulate the rotating compass needles of the Halbach array.
That's incredible.
We generate the complex rotating magnetic field purely using electricity flowing through a single atom-thick layer of carbon. And because it is powered by electricity, it is continuously tunable. We can adjust the current to dial in the exact magnetic field the qubits need with absolute precision.
Okay, the physics of that are mind-bending. But it raises an immediate, glaring, practical question for me. Understanding the math of a spherical Halbach array on a chalkboard is one thing. But how on earth do you physically manufacture a hollow, perfect sphere out of a single layer of carbon and then perfectly draw these microscopic electrical paths onto it?
You're touching on what is arguably the most disruptive part of this entire white paper. We are leaving behind the massive, multi-billion-dollar silicon fabrication foundries that companies like Intel or IBM rely on.
Okay.
We're moving into a process driven by wet chemistry, specialized 3D printing, and laser photonics.
I was reading through the fabrication section of the white paper, and it honestly reads less like a high-tech manufacturing spec and more like a recipe from an experimental cooking show.
It really does.
Let's walk through the exact materials checklist they need for the first phase, which is just a 10 milliliter batch of material. You need 0.4 grams of graphene oxide powder. You need 10 milliliters of standard deionized water. You need a tiny bit of fumed silica, some HPMC, and some calcium chloride.
That's it.
That's the entire list. It feels like you could find half of that in a high school chemistry supply closet.
It is incredibly accessible by design, but each of those ingredients performs a highly specific, complex mechanical function. Let's break down the chemistry.
Sure.
The graphene oxide, or JoGo powder, is the foundation. It's basically graphene that has oxygen molecules attached to it, which makes it easily dispersible in water. That JoGo powder is your base structural matrix, and eventually it will become your electrical conductor.
But if you just mix powder and water, you get a puddle of black ink. You can't build a hollow 3D sphere out of a puddle. It would just collapse under its own weight. So what is the fumed silica for?
Fumed silica acts like microscopic rebar. In structural engineering, you put steel rebar inside concrete to give it compressive strength. The fumed silica particles disperse through the water and lock the graphene sheets together, providing the microscopic mechanical scaffolding so the structure can bear its own weight as it's being built.
Okay. And what about the HPMC? The paper calls it a shape or tension modifier.
HPMC stands for hydroxypropyl methylcellulose. It's a fascinating polymer that imparts a property called yield stress to the fluid.
Let me guess. Yield stress means it only flows when you push it really hard.
Exactly. When the ink is sitting still in the printer cartridge, it feels almost solid. When the printer applies high pressure to push it through a microscopic nozzle, the mechanical stress temporarily breaks the polymer bonds, and it flows smoothly like a liquid.
That's wild.
But the absolute millisecond it exits the nozzle and that pressure is removed, the bonds snap back together. It instantly solidifies. This is the magic ingredient that allows you to print the curved, overhanging walls of a hollow sphere without the wet ink dripping down and collapsing.
And the final ingredient, the calcium chloride.
The calcium chloride acts as an ionic cross-linker. The calcium ions act like chemical bridges, firmly locking the layers of graphene oxide and polymers together into a stable, rubbery structure called a hydrogel.
So you mix all this up into an ink. What is the physical process of building the sphere? The white paper outlines a two-step printing and reducing process. Step 1 is direct ink writing, or DIW.
Direct ink writing is essentially highly precise robotic 3D printing. You take this yield-stress graphene oxide ink and extrude it through a microscopic nozzle about 400 microns wide onto a platform. But this isn't a normal printer bed. The platform is supercooled to negative 25 degrees Celsius.
So you are printing layer upon layer of this wet hydrogel to build the hollow sphere, but because the platform is freezing, the water inside the ink is freezing into ice the moment it touches down.
Right. You're essentially printing a sphere made of frozen, microscopic, muddy ice. And at this stage, it is completely useless as an electronic device.
Because it's full of frozen water. So how do they get the water out without the sphere collapsing? If they just let it melt at room temperature, it would turn back into a puddle.
They use a process called lyophilizing, more commonly known as freeze-drying. They take the frozen sphere and place it inside a high-vacuum chamber for 24 to 48 hours.
Okay.
In a high vacuum, ice doesn't melt into liquid water. It undergoes sublimation. It transitions directly from a solid ice crystal into a water vapor gas, completely skipping the liquid phase. The gas is safely pumped away.
Which leaves behind what the paper calls an aerogel scaffold. The water is gone, and you are left with the skeleton of the fumed silica, polymers, and graphene oxide. And it notes that this aerogel is 99% porous.
Yes, think of it as a microscopic, ultra-lightweight sponge made entirely of graphene oxide.
Mm-hmm.
It is mechanically stiff enough to hold its spherical shape, but chemically, it is almost entirely empty space.
Okay.
However, we have a major problem at this stage. Graphene oxide is an electrical insulator. It cannot carry the massive electrical currents we need to generate our Halbach magnetic field.
Which brings us to step 2, selective 3D laser reduction. This is the part that I really had to read 3 times to believe.
It's wild.
The white paper outlines using highly specific lasers, they mention, continuous wave CO2 lasers, pulsed 532 nanometer lasers, or femtosecond lasers. They use these lasers to basically draw the rotating Halbach current paths directly into the aerogel sponge.
Yes. The computer-controlled laser acts like a high-tech pen, meticulously tracing the complex three-dimensional vector paths required to create that rotating magnetic field across the surface of the sphere.
Okay, I have to push back here because I really want to understand the physical reality of this. We have just spent a day 3D printing a delicate microscopic sponge made of carbon.
Right.
It is 99% air, and now we are shooting a high-powered industrial laser at it to burn a perfectly precise 3D circuit board into it. How does the laser not just instantly incinerate the entire sponge into a pile of ash?
It's a completely counterintuitive concept, but the answer lies in the photothermal mechanism at play. The laser isn't burning the sponge in the traditional sense of combustion. You have to remember that graphene oxide is an insulator because its carbon lattice is cluttered with oxygen-containing molecules. These functional groups disrupt the electrical pathways.
So the oxygen is the roadblock.
Exactly.
Right.
When the highly focused laser hits a specific spot on the aerogel, it delivers a massive, instantaneous spike of localized heat. This heat provides the exact activation energy needed to violently rip those oxygen molecules off the carbon lattice. The oxygen turns into a gas and escapes through the pores of the sponge.
It strips the roadblock away.
Yes. And once the oxygen is gone, the remaining carbon atoms naturally, thermodynamically, seek their most stable state. They instantly rearrange and snap back into a pure, highly conductive sp2 bonded hexagonal lattice. We call this transformation reduced graphene oxide, or RGO.
That's amazing.
So precisely wherever the focal point of the laser touches, the aerogel transforms from a non-conductive insulator into a highly conductive microscopic wire.
And the rest of the porous matrix surrounding those newly forged wires?
It remains completely intact. Because the laser's focal point is so precise, the surrounding aerogel doesn't get hot enough to reduce. It stays as an insulating sponge.
Wow.
And this is a massive secondary benefit because that unlasered material is 99% empty space. It acts as a physical buffer that absorbs and dampens stray electromagnetic interference from the outside world, further shielding the inside of the sphere.
The paper specifically highlights the use of a femtosecond laser. Why is that specific type of laser so important?
A femtosecond laser emits pulses of light that last for mere quadrillionths of a second. It is unfathomably fast. Because the pulse is so short, it delivers all of its energy to strip the oxygen away before that heat has any time to spread to the surrounding structure.
That's incredible.
It's like a surgical scalpel that cuts faster than the tissue can even realize it's being burned. Furthermore, Because a femtosecond laser relies on multiphoton absorption, you can actually change the focal depth of the laser beam. You don't just have to draw on the outside surface of the sphere, you can focus the laser deep inside the thick wall of the aerogel and write conductive paths in true 3D volume.
So let's take stock of where we are. We have successfully manufactured the shell. We have a rigid hollow sphere made of a carbon aerogel. It is laced with intricate, laser-drawn superconducting wires that are carrying electrical currents to generate a perfect noise-canceling magnetic cavity inside.
Right.
It is structurally sound and magnetically silent. So what actually goes inside this pristine cavity?
The heart of the machine, the qubit processor core itself.
The white paper describes this core as a suspended bilayer graphene spin valley qubit processor. It's physically tethered inside the hollow cavity by what they call graphene nanoribbon struts. So we were still maintaining that unity of material.
Yes, the walls, the wires, and the tethers holding the processor are all carbon.
But what really made my jaw drop in Section 4 were the experimental metrics. It states that the Kramer's pair qubit T1 time is 30 to 38 seconds at 30 millikelvin.
That 38-second figure is, without exaggeration, the pivotal data point of the entire white paper. Everything else we've discussed exists just to make that number possible.
Really?
T1 time is known as the relaxation time. It is a fundamental measure of coherence. It tells us how long the qubit can maintain its delicate quantum state before it inevitably interacts with the environment, loses its energy, and the quantum information is destroyed.
To someone listening to this right now, 38 seconds sounds like the time it takes to tie your shoes or wait at a red light. It feels like nothing. But in the world of quantum computing, where giants like IBM and Google are fighting tooth and nail just to keep their qubits alive for a few hundred microseconds, 38 seconds isn't just an improvement, it is basically an eternity, right?
It's an eternity that fundamentally changes the mathematics of how we build a functional quantum computer. It changes the game for error correction.
Explain how coherence time relates to error correction. Why does a longer lifespan matter so much?
Think about current quantum computers. Because their qubits die and lose their information after a fraction of a millisecond, you can't trust them to finish a complex calculation. They are too noisy.
Okay.
So to solve this, physicists group thousands of these noisy, fragile physical qubits together and use complex software to have them constantly check each other's math and correct the errors as they happen. It takes thousands of physical qubits just to simulate one perfect error-free logical qubit that you can actually use for a program. The overhead is massive.
It's like trying to get an accurate weather report by asking 1,000 people who are all wildly guessing and trying to average out their answers.
Exactly. But if your qubit naturally survives for 38 seconds instead of a microsecond, the intrinsic error rate drops by orders of magnitude. The qubit simply doesn't make as many mistakes. Because it's so stable, the vast overhead required for error corrector plummets. You don't need 1,000 noisy qubits to make a logical one anymore. You might only need 100.
So the million-dollar question is, why does this specific design enable this 38-second eternity? What is a Kramer's pair, and why is it so impossibly stable inside the sphere?
It comes down to two major synergistic factors. The first is the intrinsic atomic nature of carbon itself. Most materials currently used to build quantum chips, like the silicon substrate or the aluminum wiring, have atomic nuclei with a property called nuclear spin.
What does nuclear spin actually do to a qubit?
Imagine every atom in the silicon wafer has a tiny, chaotic, vibrating magnet at its center. These spinning nuclei create a constantly fluctuating magnetic background chatter. We call this hyperfine noise.
Okay.
As the fragile qubit tries to maintain its state, this chaotic background noise constantly jostles it, eventually causing decoherence. But carbon-12, the specific isotope that makes up 99% of naturally occurring graphene, has a nuclear spin of exactly 0.
Zero nuclear spin. So the tiny vibrating magnets just aren't there. The environment is fundamentally atomically quieter.
Profoundly quieter. There is no magnetic chatter radiating from the substrate because the substrate is made of zero-spin carbon. That alone gives you a massive boost in coherence time. But the second factor is the specific type of qubit they are using, a spin valley Kramer's pair in bilayer graphene, or BLG.
I know a normal qubit relies on the spin of an electron, usually pointing up or down to represent a 1 or a 0. But what is the valley part of a spin valley qubit?
In a complex crystal lattice like bilayer graphene, electrons don't just have spin. Because of the hexagonal structure of the carbon atoms, the energy landscape of the material looks like a mountain range with deep valleys. The electron's momentum state dictates which specific valley in the lattice it occupies. So an electron is a spin state and a valley state.
Okay, so a valley is literally a local minimum in the energy landscape of the carbon crystal.
Correct. Now here is where the spherical Halbach array comes into play. By using that perfect ultra-uniform magnetic field generated by our hollow shell, we can apply a very precise force known as Zeeman splitting to the electrons.
Zeeman split.
This highly tuned magnetic field allows us to precisely lock the energy levels of the electron's spin and its valley together into a combined protected state. This locked state is called a Kramer's pair.
Why does locking them together protect them?
Because of symmetry. Once the spin and the valley are mathematically locked into a Kramer's pair, environmental noise has a terribly hard time disrupting it.
Wow.
For the qubit to accidentally flip and lose its information, a random burst of thermal or magnetic noise would have to hit it with the exact right amount of energy and the exact right momentum to flip both the spin and the valley simultaneously. The probability of that happening randomly is incredibly low.
It's locked in tight.
The quantum state becomes heavily armored against environmental disturbances. That combination, the armored Kramer's pair sitting inside a perfectly quiet zero-spin carbon vacuum, is how you achieve 38 seconds of coherence. Furthermore, the white paper notes this stability allows for a single-shot readout fidelity of greater than 99%.
So, to summarize the core, we have incredibly stable qubits, heavily armored by their spin valley locking, sitting inside a perfectly quiet magnetic cavity, completely isolated from any thermal mismatch because the entire structure is made of carbon.
Yes.
It sounds flawless. But there is a massive catch here. To keep those armored qubits stable for 38 seconds, the white paper explicitly states they need to be kept at an electron temperature of 30 millikelvin.
Yes. That is barely a whisper above absolute zero.
But hold on a second. At the very beginning of this deep dive, we made a promise to the listener. We promised we wouldn't use that massive 26 kilowatt golden chandelier.
Right, we did.
We promised this device operates without a giant dilution refrigerator. If we don't have a giant room-sized freezer, how on earth are we getting the qubits down to 30 millikelvin?
This is where the white paper introduces a paradigm shift in thermodynamics. We are fundamentally moving from macroscale cooling to microscale on-chip refrigeration.
Okay, let's really unpack this because the traditional approach to cryogenic cooling is incredibly blunt. A dilution refrigerator works by cooling the entire physical environment.
Right.
It cools the outer vacuum chamber, the copper plates, the gold plating, the miles of coaxial cables, the silicon chip, and the qubits themselves, all the way down to 10 or 20 millikelvin. The quantum sphere completely abandons that global cooling approach. Instead, it relies on a compact 4-Kelvin pulse tube cryocooler and microscopic on-chip refrigeration.
We need to clearly distinguish between these two temperatures because it is the key to the entire power-saving architecture. A 4-Kelvin pulse tube cryocooler is not exotic science fiction technology. It is a standard, relatively compact piece of cryogenic equipment.
Okay.
It is commercially available, fits easily on a laboratory benchtop or inside a small server rack, and it uses roughly 5 to 10 kilowatts of power. The quantum sphere architecture places the entire 3D printed graphene shell and the qubit processor inside this manageable 4-Kelvin environment.
But 4 Kelvin is 4,000 millikelvin. To you and me, 4 Kelvin is unbelievably cold. But to a delicate Kramer's pair qubit that needs to be at 30 millikelvin, 4,000 millikelvin is basically a roaring furnace. The heat would destroy the quantum state instantly. So how do we bridge that massive temperature gap without a bigger fridge?
We change what we are actually cooling. In a dilution fridge, you cool the entire physical structure of the chip. In the quantum sphere, we only cool the electrons themselves, right where they sit in the quantum dot at the center of the shell.
Yeah.
We don't cool the carbon walls. We cool the quantum system itself.
Ah.
The white paper outlines two specific, highly advanced on-chip cooling methods to achieve this targeted refrigeration. The first method is called embedded tunnel junction coolers.
What exactly is a tunnel junction cooler, and how does it fit onto a microscopic graphene chip?
During the clean room fabrication process, the engineers deposit tiny, microscopic superconducting contacts, usually made of aluminum or niobium, directly onto the graphene nanoribbons just outside the qubit core.
So these tiny metal contacts are sitting right next to the qubits.
Right. Now, in any pool of electrons, even at 4 Kelvin, some electrons are jumping around with high energy, we call them hot electrons, and some are sluggish with low energy, the cold electrons.
Okay.
When you apply a very specific tiny electrical voltage across these superconducting contacts, you induce a phenomenon called quantum tunneling. But because of the energy gap of the superconductor, this tunneling is highly selective.
Selective in what way?
The physics of the junction acts like a strict bouncer at a club. It only allows the highest energy, hottest electrons to tunnel out of the graphene qubit core and into the superconductor. The low energy, colder electrons don't have enough energy to make the jump, so they are left behind.
It's a microscopic electron filter.
Right.
It actively sucks the hottest particles out of the pool, which naturally lowers the average temperature of the electrons left behind. The white paper notes that this specific mechanism transfers heat at an astonishing rate of negative 115 Kelvin per volt.
Exactly. It selectively evaporates the hot electrons, constantly chilling the qubit core down toward that 30 millikelvin target, while the surrounding carbon structure stays at a balmy 4 Kelvin.
That's brilliant.
And as impressive as that is, the second on-chip cooling method is even more exotic: on-chip quantum absorption refrigerators.
Yes, I read this section and it sounded like pure magic. The paper describes these refrigerators as artificial molecules pumping heat away using controlled microwave noise. How can blasting something with microwave static possibly cool it down?
It relies on the complex principles of quantum thermodynamics. The engineers fabricate tiny artificial quantum structures directly into the graphene lattice, physically adjacent to the main processor. You can think of these structures as sacrificial qubits. They are designed with highly specific, tunable energy levels.
Okay, so we have these sacrificial artificial molecules sitting next to our main computer. What does the microwave noise do?
By feeding these artificial molecules a stream of controlled microwave noise through the graphene wiring, you drive a microscopic thermodynamic cycle. The microwave noise provides the energetic work necessary to force a transaction.
Okay.
It allows these artificial molecules to reach over, absorb a heat photon from the cold qubit core, and forcefully dump that heat photon into the warmer 4 Kelvin surrounding environment.
So it is quite literally an autonomous, solid-state quantum air conditioner that requires absolutely no moving parts, no liquid helium pumps, and no compressors. It just runs on a microwave signal.
It's brilliant. Let's make sure we have a clear analogy for the listener. Think of a massive office building in the summer. A dilution refrigerator is like trying to keep a single server rack in the basement cold by setting the entire building's central AC to minus 40 degrees. It requires a massive industrial power plant to run, and the whole building freezes.
Right, whereas the quantum sphere approach is like keeping the building's central AC at a brisk, manageable 65 degrees, and then attaching a microscopic, hyper-efficient, solid-state thermoelectric cooler directly to the actual microchip on the server rack in the basement.
That's a perfect visualization. You manage the heat precisely where it is generated, locally, rather than trying to overpower the thermodynamics of the entire macroscopic environment.
Yeah.
And if we connect this to the bigger picture of the industry, managing heat locally is what truly unlocks commercial scalability. The power comparison laid out in the white paper is staggering.
Let me pull those numbers up. The entire quantum sphere prototype, including the 4 Kelvin pulse tube cryocooler running in the background, uses a total of 5 to 12 kilowatts of wall plug power. To put that in perspective for you listening, 5 kilowatts is roughly what your standard electric kitchen oven uses when you are baking a pizza.
And you compare that to the massive IBM and Google systems, which are drawing 10 to 26 kilowatts of continuous power for systems that deliver a fraction of the performance and massively lower coherence time.
It's a huge difference.
With the quantum sphere, you are getting vastly superior quantum stability, you are cutting your electricity bill in half, and the entire apparatus fits on a benchtop instead of requiring a dedicated warehouse space.
And because you aren't completely reliant on the massive bespoke supply chain required to build and maintain a giant dilution refrigerator, the speed at which you can innovate and test new designs accelerates exponentially. Which leads us directly to the timeline proposed in the white paper.
The prototype roadmap outlined here is, frankly, aggressive. When a major legacy tech company announces a new quantum architecture, their roadmap usually stretches out a decade into the 2030s. The Quantum Sphere white paper outlines an accelerated roadmap to build a functional prototype in a matter of months.
And they're proposing doing this with a core team of just 4 to 6 people. What physical equipment do they actually need to pull off this timeline?
The infrastructural requirements are surprisingly modest. For a field normally dominated by billions of dollars of capital expenditure, they need access to a standard university-level cleanroom. They need a Van der Waals transfer station, which is a specialized microscope rig used to precisely stack 2D materials like graphene. They need the direct ink writing 3D printer we discussed, and they need the laser systems, specifically the femtosecond or pulsed lasers, for the photothermal reduction.
Let's walk through the actual step-by-step milestones to see how fast this moves. The project kicks off with M0 to M1, which covers weeks 2 through 4. During this month, the team focuses on locking in the exact chemical formulation of the graphene oxide ink.
Right.
They run the complex Halbach magnetic field simulations on standard multi-physics software like COMSOL, and they design the electron beam lithography masks that will be used to pattern the quantum dots in the clean room.
That first month is purely digital prep work, chemistry calibration, and simulation. The physical reality begins in M1 to M2, weeks 3 and 4. This is where the two distinct manufacturing tracks happen in parallel.
Good track.
Track 1, they fire up the 3D printer, print the wet hydrogel graphene aerogel shells, freeze-dry them in the vacuum chamber, and use the laser to reduce the Halbach magnetic patterns directly into the shell wall.
In track 2.
Track 2, meanwhile, inside the clean room, another part of the team uses the van der Waals station to physically assemble the actual bilayer graphene double quantum dot, the qubit core itself, encapsulating it in protective layers of hexagonal boron nitride.
And they also deposit those tiny aluminum superconducting tunnel junction coolers during that cleanroom step. Then the whole project comes together in M2 to M4, weeks 6 to 8, assembly time.
This is the critical integration phase. They take the incredibly delicate qubit core from the clean room, insert it into the hollow cavity of the laser-printed shell, and carefully suspend it using the carbon nanoribbon tethers.
Wow.
Then, they seal that entire spherical assembly inside the compact vacuum enclosure attached to the standard 4 Kelvin pulse tube cooler. They flip the switch.
They turn on the electrical currents to generate the Halbach magnetic field. They activate the microscopic tunnel junction coolers to pull the heat out of the electrons, and they begin measuring the first coherent qubit oscillations.
Think about the pace of that. Within just 2 months of starting the physical build, they expect to achieve a working, highly coherent quantum system, completely bypassing the need for a dilution fridge.
That's unbelievable.
And then M4 to M6, the final stretch of the prototype phase, is entirely dedicated to scaling that single qubit up to 2 to 4 coupled quantum dots inside the core and demonstrating entanglement.
Entanglement being the quantum phenomenon where the state of one qubit is fundamentally invisibly linked to the state of another, which is the absolute baseline requirement for doing any actual quantum computation. So what does this aggressive timeline actually mean for the industry?
It's massive.
We are talking about a timeline measured in months, not decades. Is this unprecedented speed entirely because we cut out the dilution fridge from the critical path?
Cutting the dilution fridge is certainly a massive logistical advantage.
Yeah.
If you are building a traditional quantum computer and you need a custom dilution refrigerator, you are looking at a procurement lead time of a year or more just to get it delivered.
Right.
If you break a critical component during testing, you might wait 3 months for a replacement part from a specialized vendor. By eliminating that macro-scale infrastructure, you remove the single longest logistical delay in the entire industry.
But that's only half the story, isn't it?
The other reason this moves so fast is because the fabrication cycle for 2D materials like graphene is intrinsically rapid.
Because, as we discussed earlier, the graphene oxide ink is basically a chemical commodity that a grad student can mix up in a beaker in an afternoon.
Yes. Look at the iteration cycle. Printing the aerogel shell takes a few hours. Freeze-drying it takes a day or two. Laser patterning the magnetic circuits takes minutes.
It's so fast.
Let's say the team builds the prototype, and they realize the magnetic field simulation was slightly off, or the shell wall isn't thick enough. In traditional planar silicon manufacturing, if you make a mistake, you have to redesign the chip, send the design to a massive silicon foundry, and wait 6 months and pay millions of dollars for them to ship you a new batch of wafers.
But with the quantum sphere architecture...
With this architecture, if you make a mistake, you just adjust the laser toolpath in your software, print a new aerogel sphere on the benchtop, laser it, and test it the very next day. Your entire design, print, test iteration cycle is reduced from half a year down to less than a single week.
That capability for rapid iteration is how you achieve exponential technological progress. But let's take a step back and look at the end game here. A benchtop prototype with 2 or 4 qubits is an amazing physics experiment. It proves the concept. But the true goal of quantum computing, the holy grail that will allow us to simulate entirely new pharmaceuticals atom by atom, break the world's most complex cryptography, or model global climate systems with perfect accuracy, requires millions of qubits working together. You can't change the world with 4 qubits.
No, you can't.
How does a single grapefruit-sized graphene sphere sitting on a benchtop scale up to a machine with 1,000,000 qubits?
That exact question brings us to the final and most ambitious section of the white paper, the Quantum Dyson Sphere. This is where the elegant benchtop architecture evolves into a true industrial-scale computational powerhouse.
Now, quantum Dyson sphere sounds incredibly intimidating. In classic science fiction, a Dyson sphere is a massive megastructure built completely surrounding a star to capture all of its solar energy. What does that term mean in the context of microscopic carbon computing?
In this context, it refers to the 3 to 4 year pathway to scale the architecture up to commercial viability. The concept is that instead of manufacturing a single isolated hollow shell, you use those 3D printing and laser techniques to manufacture 10 to 50 nested concentric graphene aerogel shells.
Imagine a massive, complex set of Russian nesting bells. A sphere, perfectly fitted inside a larger sphere, all made of laser-patterned carbon, and the white paper states that this entire 50-layer nested structure physically fits into a footprint about 1 to 2 meters in diameter.
That's roughly the size of a standard laboratory bay or a large server cabinet. It is dense, and crucially, each one of those nested shells is carrying its own intricate laser-patterned rotating surface currents. By precisely tuning the currents across all 50 shells, you generate a massive series of overlapping, perfectly uniform magnetic cavities throughout the entire three-dimensional volume of the structure.
Okay, nesting them sounds cool, but why is that the solution? If we need more qubits, why not just build one giant, flat, 2-meter-wide graphene board and put all the qubits on that? How does nesting spheres solve the scaling problem?
Remember at the very beginning of our conversation, we established that the fundamental limit of current planar chips like IBM's Condor is the 2D wiring bottleneck. When you have a flat chip, you simply run out of perimeter edges to route the microwave control lines into the center. It's the traffic jam.
Right.
If you just built a bigger flat board, the traffic jam would just get proportionally worse. The quantum Dyson sphere completely bypasses the planar limitation because it utilizes true, unconstrained three-dimensional connectivity.
The white paper mentions something called radial spoke planes connecting these nested layers. What exactly are those?
Between the nested spherical shells, the engineers grow or transfer flat planes of bilayer graphene heterostructures that radiate outward from the center, exactly like the spokes of a bicycle wheel connecting the hub to the rim. These radial spokes structurally and electrically connect the different concentric layers.
Why is that important for the qubits?
Because it means a qubit sitting on shell layer number 2 can directly talk to a qubit sitting all the way out on shell layer number 15 by routing its microwave signals straight up a 3D radial pathway.
Yeah.
It doesn't have to navigate through a crowded 2D maze of other qubits.
Going back to our city analogy, it's like moving from a sprawling, flat city grid with terrible traffic, where everyone is forced to use the same 2-lane perimeter highway, and moving into a massive, perfectly organized 3D space station.
Exactly.
In the space station, every single room is connected via vertical elevator shafts and horizontal corridors in all directions. You can just take the elevator straight up to the floor you need.
When you unlock that z-axis, the available physical volume for housing qubits explodes. Because the carbon quantum dots themselves are microscopically tiny, the paper notes they occupy a pitch spacing of just 100 to 500 nanometers. The sheer surface area and internal volume of a 2-meter nested sphere can physically accommodate billions of individual physical qubits.
Billions of physical qubits is an unfathomable number. But as we discussed earlier with error correction, physical qubits don't directly translate to computing power. We need to translate those raw physical qubits into logical qubits.
Right.
A logical qubit is the error-corrected, highly stable mathematical construct that actually runs the algorithms and does the math.
This is where all the different engineering innovations of the quantum sphere cascade together into the final outcome. In a typical planar system, because the physical qubits are so noisy, fragile, and prone to decoherence, you need to dedicate 1,000 physical qubits to constantly check and error correct a single logical qubit, a ratio of 1,000 to 1.
But because our Kramer's pair qubits inside the sphere are armored by the spin valley physics and protected by the pristine magnetic field and insulated by the zero-spin carbon lattice.
Because they have a 38-second coherence time instead of a microsecond coherence time, the error correction overhead drops dramatically.
Yeah.
The white paper projects that the ratio drops from 1,000 to 1 down to just 100 or 200 physical qubits per logical qubit.
That's huge.
So if your 2-meter Dyson sphere can hold, say, 100 to 200 million physical qubits in its massive 3D volume, You can reliably extract 1 million fault-tolerant logical qubits.
And 1 million logical qubits is the universally accepted threshold for world-changing quantum computing. It's the point where you can actually run Shor's algorithm to break RSA encryption or simulate the exact chemical binding of a new drug.
It's the holy grail.
But practically speaking, how on earth do you manufacture a 2-meter-wide nested carbon sphere? You certainly can't fit a 2-meter object inside a university clean room or under a standard laboratory 3D printer.
You don't build it in a clean room. To reach the Dyson Sphere scale, you shift from delicate boutique laboratory fabrication to industrial robotics.
Okay.
You scale up the direct ink writing process. You use massive robotic arms, similar to the ones used to manufacture cars, to extrude the graphene oxide hydrogel and print modular, meter-scale hemispherical shell segments in parallel across a factory floor.
So you print it in pieces, like assembling a ship.
Yes. You use large bed femtosecond laser scanners to rapidly pattern the magnetic currents across those large segments. Then, you physically assemble the modular pieces together. And to ensure the electrical currents flow perfectly across the seams where the pieces join, you use 3D printed graphene via essentially tiny carbon bridges to weld the pieces together with perfect electrical continuity. It becomes an advanced modular manufacturing assembly line.
And what about the cooling? If you have 50 layers of shells and 100 million qubits, doesn't the inside get too hot?
Because you are distributing millions of those microscopic tunnel junction coolers all throughout the radial spoke layers, the entire megastructure actively cools itself. The internal core stays locked at a perfect 30 millikelvin, even though the room outside the sphere is just running standard 4 Kelvin pulse tube commercial refrigeration.
It is a breathtaking vision of the future of computing. When you look at the whole roadmap, the scale of the innovation is almost hard to process. We started with a simple high school chemistry checklist of graphene oxide powder and water. We turned that into a microscopic 3D printed aerogel sponge. We used lasers flashing in quadrillionths of a second to draw invisible magnetic fields. And we scaled that up to a self-cooling million-qubit Quantum Dyson Sphere that completely rewrites the rules of scaling.
It's an important reminder of how technology actually advances. This white paper proves that the massive limitations we thought were fundamental to the physics of quantum computing, the massive 26 kilowatt power draw, the huge room-sized dilution fridges, the unavoidable 2D wiring bottlenecks weren't fundamental limits of physics at all. They were just limits of our initial planar engineering choices. When you fundamentally change the materials, the impossible bottlenecks just disappear.
As we wrap up this deep dive into the quantum sphere, I want to connect this incredible physics lesson back to you, the listener, and why this matters for the future. We constantly see headlines in the tech press about massive trillion-dollar tech giants building bigger, more expensive, more power-hungry freezing vaults. They are in an arms race to build a bigger chandelier.
They are.
But the real quantum revolution, the one that might actually put a fault-tolerant, world-changing quantum computer in every major hospital and research facility in the world, isn't going to look like a giant freezer. It might be quietly 3D printed in a 4-person university lab using a wall plug that draws the same power as a pizza oven.
That is the ultimate promise of this architecture. It democratizes the technology. It proves that scaling quantum computing isn't solely a brute force infrastructure problem. It takes quantum computing out of the exclusive realm of billion-dollar megacorporations and puts it directly into the hands of agile, materials-focused engineering teams.
And that leaves us with a final provocative thought to mull over as we close out. Think about the geopolitics and the economics of the tech industry right now. If the graphene ink is basically a commodity you can mix in a beaker, and the 3D printers and femtosecond laser equipment are already standard tools in modern university fabrication labs around the world, what happens to the global tech balance of power when a 4-person lab team operating on a shoestring budget can build a world-class coherent quantum computer in just 6 months? If you don't need $1 billion to build a quantum computer, is the quantum monopoly about to be completely broken?
That ultimately is the million-qubit question. The barriers to entry are collapsing.
So the next time you read an article about a new quantum computer, don't picture a massive 26 kilowatt golden chandelier. Picture a perfect, silent, invisible magnetic sphere. Thanks for joining us on this deep dive.